Okay, so this tutorial is going to highlight some of the important aspects of a formal lab report using the formal report that I have done here. So first off, besides the obvious, my experiment, the date, the class, I have a title here. Now this title should be descriptive in terms of what your experiment is trying to do. So in this case, for the atomic spectra lab, I have the atomic spectrum of hydrogen because that's what I'm mainly interested in when I'm writing this formal report. That's my main results that I'm trying to convey. So my first section is an abstract. I can see here by highlighting my abstract that it is 148 words. So that's about right. You really don't want more than 150 words. If you have more than that, maybe it's because you have a lot of data, but unless you have a ton of data to report, you really shouldn't be more than 150 words. So let's go ahead and read that together. Spectra are the fingerprints of atoms and molecules. They are found by diffracting the light emitted by an excited electron or molecule. Once diffracted, the emitted photons are separated into their respective wavelengths, and the quantum number of the transition as well as the energy may be found. The spectrum of hydrogen was analyzed spectroscopically and was determined to have three characteristic emissions in the visible spectrum. The first was red and had a wavelength, lambda, of 151 nanometers. Now I'll point out here that this is the correct number of significant figures that is determined by our spectroscope. You may only be able to read to 2, but I think it's pretty safe to say that you could get 3 out of that. So just be aware, those are the correct number of significant figures. The next was blue-green and had a wavelength of 480 nanometers, again, correct significant figures. The last was a purple line at the wavelength 410 nanometers. These values are all within 2% of the literature values. I have a superscript here for the citation of the literature value, which I will put in my bibliography at the end, indicating the data collected were highly accurate. Now I'll point out here that data is a word that is plural. The singular of data is datum. That would be one data point. So it's kind of a confusing word, but data is plural. So when we say data were collected, we're talking about more than one data point. However, there is a fourth characteristic emission for hydrogen that was not observed, leading to the conclusion that the spectroscope may not be sensitive enough for the required measurement. So what is our abstract telling us? It is telling us what we're going to be talking about, right? This whole first part up here is telling us the kind of general idea of what we're looking for. This section in here, the spectrum of hydrogen was analyzed spectroscopically, is telling us how we analyzed the spectrum. So what tool did we use? And what data did we collect? 3 characteristic emissions. Now we're going to go ahead and report the values that we came up with. The most important ones. Obviously not every single measurement is going to be important, but in this case we'll report all of our data, and then we're going to talk about how good that data was, and then lastly we're going to talk about if there were any problems with the data. And that's it. That's all you need to do. If there aren't any major glaring problems with your data, then this part is not necessary. You would just leave it with this last sentence here, and that would be fine. Okay, so moving on to the introduction. I'm not going to put too fine a point on reading this whole thing, but suffice it to say it's background information. There'll just be a couple of things that I will point out to you. The idea of splitting light into its component parts was pioneered by Isaac Newton in the 17th century. Using a prism, Newton was able to demonstrate that white light was actually comprised of all colors of light. From Newton's discovery, it would be a few centuries before scientists would discover that there was more electromagnetic radiation than just the visible spectrum. Figure 1. Now, what does that mean? I'm citing this figure. The figure title, the figure name right here is figure 1. That's always going to be capitalized when I cite that. Many great scientists in the 1800s developed the theory of electromagnetic radiation. So now we have our figure. It's just a picture that I copied from the internet. I should have probably cited that, but I'm not going to worry about that right now. A citation on this would go either right here or at the end. And then I have a description of what can be found in that figure. So the idea of a figure title and a figure description is that you want to make sure that the figure can stand alone. So if I didn't have the body describing the context of why this figure is here, I could just look at the figure and understand exactly what I was looking at. So that's the idea of having this description down below. I mean, in this case, it's fairly obvious what we're looking at. We know, we've seen this figure many times before, but the point is that there will be more abstract figures that you'll need to explain a little bit more. So just get into the habit of doing this, and it will make everybody's life easier when they're reading your papers. Okay. So, Anders Engström further refined this idea in the 19th century with the discovery of the atomic spectrum of hydrogen. Today, spectroscopy is used for a variety of exciting research, such as determining the composition of stars in the Milky Way and other distant galaxies. It is also used to determine the functionality of compounds to verify composition. The relationship between the energy level and the quantum transition was first developed by Johann Balmer in 1885 and was generalized by Johannes Rydberg 3 years later to the now famous Rydberg equation. And now I've cited my equation here, equation 1. Again, this is a title, so it should be capitalized, capital E equation. And then I've used the math type tool, this math type tool up here, to put in my my equation. So I'm going to go to the equation tools and just go over briefly how I did that. So here I can add a fraction. So this guy right here is a fraction, so that's what I did to get 1 over lambda. In here I added a symbol by going to Insert, Symbol, Advanced Symbol Browser. Takes some time sometimes to load. And there I picked lambda, and I inserted that, and then I did a space, equals, capital R, parentheses. I came up here and made another fraction using this same setting. And then down here, it gets a little more tricky. So normally I would just have one box here, and what I've done is gone to eScript and first inserted this guy here for my subscript. Then I can go ahead and highlight both of these guys together and put in my superscript. So I would just click on this guy here. Alright, and then minus, and then my other fraction, and then again I would put in my eScripts in the same fashion. And then the way that I like to do this, although you're free to pick your own way, is I just left-hand format this and put my equation number here. So this is shorthand for equation 1 in the same way that my superscript was shorthand for a citation that will be found in the references. Okay, so that is done. Now we are going to name our constants, and we're going to talk about what the equation is comprised of. So we have R is the Rydberg constant, and 1 is the lower quantum number, and 2 is the higher quantum number, and lambda is the wavelength of the emitted or absorbed photon. Although this equation was developed in 1888, it was completely empirical, meaning there was no notion of quantization of energy. It was simply known that this equation worked. So an empirical formula, suffice it to say, is just an equation that has no theoretical foundation. Meaning, in this case, there was no quantization of energy. Nobody had any idea about subatomic particles in 1888. That discovery hadn't been made yet. So they had found this equation in a kind of ad hoc way. Like, well, it seems to work all the time in this way. So we'll go with it. This will be the equation that we'll use. But it wasn't actually justified until far later. Okay, so that's what empirical means. In Rydberg and Balmer's time, the model of the atom was John Dalton, 1805, and described the atom as an indivisible quantity. Again, subatomic particles were not discovered until 1897. It would take another 25 years for the Bohr model in 1913 of the atom to be introduced, which incorporated the notion of discrete energy levels in atomic orbitals. Using the Rydberg equation, it is possible to find the quantum number of the transition associated with the spectral line at some wavelength. This principle will be demonstrated herein. So I've got a little bit of background information, I've described the equation that I'm going to use in my results, and I've left off by saying that's basically what I'm going to do, using no personal pronouns and never talking in the I sense. This is not what I am going to demonstrate. It's the principle that will be demonstrated. So it's this kind of passive language that we use when we're talking about what's going to happen in the experiment. Okay, and this whole section is in a mixture of kind of past tense and passive present. So you're kind of flipping back and forth between that. You kind of have to be in the past tense when you're talking about things that were, but you're also able to kind of talk about things that will be to a certain extent, to a lesser extent. Okay, so now our results section. Before examining the atomic spectra of various elements, a flame test was done to demonstrate the visible emission of photons of various wavelengths in the visible spectrum by excitation. So again, we are now into past tense. The flame test was done. This is because we are talking about an experiment that we've already done. So this data is summarized in Table 1. Again, Table 1 is a title for the table, which is here. We want to make sure that we capitalize that. Now I've got my compound name here with proper subscripts. We can go ahead and highlight this and see that if we click here on the A with a little 2 next to it, it will give us a subscript. And then I've put in all the different colors, and I've got a description for my table so that it's understood. If we just looked at the table without any of the body of the writing, we would understand what this table was showing us. Alright, the spectra of hydrogen, helium, mercury, nitrogen, neon, and water were examined. Again, these are spectra plural as opposed to spectrum, which is singular. Spectra of all of these different elements. The spectrum of hydrogen provided 3 spectral lines, Table 2, which is going to be down here. Okay, using the wavelengths of these spectral lines and rearrangement of equation 1, the initial quantum number N2 for the transition associated with each emission may be assessed. Equation 1 may be rearranged as followed. Now, I've gone ahead and done multiple steps using math time. I basically just copied my first one and then rearranged it, so it's a little bit less work. It doesn't matter if you have it set up in a traditional sense of having N2 be on this side of the equation, since that's what we were looking for. It's really not important, as long as you have everything here and it's clear. And you need to make sure that you are labeling each equation in case you need to write more about that equation in the body of the text. All data for hydrogen emissions are detailed in Table 2. So here's my Table 2. I have my color of the spectral line, the wavelength of the associated spectral line, and then the N transition, and then my table description. And that's it. Those were all of my results, so pretty small section for this experiment. So for the discussion, the data given in Table 2 may be compared to the literature values. Again, I'm going to cite this because it hasn't been a while since I talked about it. For the known spectral lines of hydrogen. For the red emission at 651 nanometers, the literature value is 656.2 nanometers. This is a percent difference of 0.79%. Now, I don't need to show the calculation of how I got this. It's a very simple calculation, so it's not required of you to show me that you know how to do this kind of simple calculation. Okay, so for blue-green emission, the given literature value is 486.1 nanometers, which is 1.25% difference from the experimental value of 480. Again, correct significant figures here, nanometers. The literature value for the violet emission is 410.1 nanometers, which is a 0.02% difference from the experimental value of 410 nanometers. Again, correct significant figures. Based on this evidence, it would seem that the data collected were not only precise, but also accurate. However, there's a fourth spectral line for hydrogen given in the literature, blue-green at 434.0 nanometers. This spectral line was not evidenced in the experiment. This could be due to insufficient sensitivity of the spectroscope used. In addition, this error could be due to experimenter error in viewing the spectrum. It would be advisable to repeat the experiment several times and potentially using a more sensitive spectroscope for measurement to confirm the spectral line for hydrogen, the fourth spectral line for hydrogen, and potentially use, excuse me, I'm correcting myself. So this is a really good way, I know it sounds really stupid, but really good way to edit your own work is to read it out loud. Every time you read something out loud, you'll realize probably 50% of your mistakes, if not more. The second way is to have somebody else read it. They don't really need to know what the heck you're talking about in order to be able to tell you if you made a simple mistake with grammar or with punctuation or something like that. So, get your, older brother or your mom or someone else, your buddy, to just read over what you've got. Or you can use your lab partners, they're a resource for you. So see what they think. See if they think that your, English is correct, your grammar is correct, and your punctuation is correct. Okay, so the discussion section, what is it? First thing we're going to do in the discussion section is go ahead and reiterate our data. So that's what I've done here. I've kind of mashed up my reiteration of the data that I just talked about in the results section with my percent difference from the literature values. It's not necessary to do this way, but you have to repeat the data that you just gave me up here. I know that this sounds redundant, but this is just the way that it's done. You always start off a discussion section by repeating, this is the data that I found, and then you qualify how good is that data. So the next few sentences, I qualitatively talk about whether or not my data was good. So yes, it was good, and it was also accurate. Now is when I start talking about any potential errors. In this case, I already know what my error was, so it's very cut and dry. I didn't see this spectral line. And so then you want to hypothesize why this error might have occurred, and then talk about what could be done going forward to fix that error. And that's it. That's the discussion section. So this is kind of a simple example that can definitely get more complex than this, but I think most of the important things that need to be talked about we've talked about here. One other thing to mention in the discussion section is that this is kind of a passive present. So the tense on this section is going to be different than the results section. This is not what you did. this is what you have. So this tends to be a passive present, and even some future tense towards the end will be all right there. Okay, so that's that. Thank you very much. Bitch ass.